Hello, everyone. I'm going to talk about black hole solutions in extended metric Palatini gravity. I started my PhD almost 4 years ago with Durmuş Hoca at Sabancı, but unfortunately, in the third year of my PhD, we lost him. It was a great honor for me to meet him, but unfortunately, the opportunity to work with him was very short for me. First, I will explain extended metric Palatini gravity very fast because Behnam Hoca described the model, so I will just pass to black hole solution soon. So in general relativity, we can have two formulations, metric formulations and Palatini formulations. In metric formulations, we write Einstein-Hilbert action with this form, which has Ricci scalar as a function of metric only. So we have only one independent variable, and we assume metric compatibility from the beginning, which leads to Levi-Civita connection. Then we can get one field equation, which is Einstein field equation in vacuum. But in Palatini formulation, we have the affine Ricci scalar, which is a function of metric and affine connection. And then no metric compatibility is assumed from the beginning like here. And then affine connection, instead of Levi-Civita, we have affine connection. Then we get two field equations. Variations of the action with respect to metric gives us Einstein field equation, and variation of the action with respect to affine connection gives us this metricity condition. So all the information can be hidden in the action, and we don't need to assume from the beginning this metricity condition. Now we want to extend this Palatini formalism and substitute the affine Ricci scalar with a function of it, which here is the antisymmetric part of this affine Ricci scalar. The reason that we choose this combination will be clear soon. Then we add to this setup also the metrical curvature, and we call this setup extended metric Palatini gravity. So in this model, if we consider the difference between affine connection and the Levi-Civita connection, which is written in terms of the non-metricity tensor, and the non-metricity tensor is just a covariant derivative of the metric, then we can rewrite this action in this form, which is this is the metrical curvature, and y mu is, we call it geometric Prokop field, which comes from non-metricity. So this y mu is just the non-metricity of the spacetime. So this system, the action that we chose reduces to general relativity plus a massive vector field y mu. This system in the literature is known by Einstein-Proca system, but we call it Einstein geometric Proca because in the Einstein-Proca system in the literature, they considered energy momentum tensor for a massive vector boson, but here we didn't do that. We just considered the non-metricity of the spacetime, and the source of this field is the geometry itself. And this system was studied as Behnam Hoca described in the geometric dark matter paper. So this extended metric Palatini gravity reduced to Einstein geometric Proca system, and we add to our system cosmological constant to be able to get a black hole solution. So you see here, non-metricity is the only source of deviation from general relativity. And the purpose is to study this non-metricity tensor using the black hole solution of the model. So then we get the field equations from variation of the metric with respect to variation of the action with respect to metric and variation of the action with respect to geometric Proca field. We get the Proca equation. For constructing the black hole solution, we consider our metric ansatz as a spherically symmetric with two metric functions HR and FR, and this is the form of the Proca field as a function of R. Then we get the Einstein field equations, and to solve these equations, first, if we consider, oh, this is wrong. If we consider flat spacetime, we get this solution for Proca field, and we see that we cannot get a finite Proca field, a large R or a small r, But when we add cosmological constant to our system, or when we go to the ADS background, then the solution for PROCA gets this form, which doesn't have the problem that we had here. And Q1 and Q2 are constants here, and sigma is a parameter related to the mass of the PROCA field. And to avoid some tachyonic behavior, we limit it between 0 and 1. Then in the limit, when sigma goes to 1, this PROCA solution reduces to this form, which means that this Q is like an electromagnetic charge. And then we go to calculate the back reaction of this PROCA field on the geometry, and we see that the metric is modified by these terms, and these constants have this form. So after substituting them in the solution, we see the final form of the metric is like that, and we call this Einstein geometric PROCA ADS black holes. Now let's look at the limit case. When charge is 0, Q1 is 0, and when R is much smaller than L was the ADS scale size, we get the solution becomes this form, which is the Schwarzschild black hole. Then we studied the structure of the singularity. When we calculate Kirschmann scalar, we see that it shows two singularities. One primary singularity at the origin, and there is a second singularity where the GTT goes to 0. And the place of the second singularity depends on the charge of the black hole. And in the limit, when sigma goes to 1, actually when sigma goes to 1, it corresponds to a massless electromagnetic-like geometric vector field. In that limit, Kirschmann scalar reduces to Kirschmann scalar of the Schwarzschild plus this extra term. So we can say that black hole solution of this model possesses structures beyond the Schwarzschild case, and the second singularity is a direct signature of the PROCA field or non-metricity of the spacetime. Then we studied the horizon radius. Here you can see that horizon radius according to the sigma for different values of Q1, which was one of the charges. And when Q1 is equal to 0, we recover the horizon radius of Schwarzschild black hole. And as the charge increases, the horizon is shrinking. The same thing is also happening here for here, the value of another charge is changing. Then an observational test for the theory can be optical properties of our solution, because the light is affected by the space-time curvature and we can get a black hole shadow. For this aim, we study photon motion and shadow radius, and we can get photon radius and shadow which follow the same pattern as horizon radius. And here we see that the photosphere reduces to the photosphere of Schwarzschild black hole when the charge is 0. And again, we see the shadow radius of Schwarzschild black hole when charge is 0. And at the end, the purpose was to put some constraints on the model parameters, which we did using the observational data on Sagittarius A and M87 black holes. Here you can see the constraint between Q1 and Q2 for some fixed values of sigma. And here, again, the constraints on Q1 and Q2, the charges of the black hole, when sigma is going in the limit to 1. And we see that in the limit case, the constraints between Q1 and Q2 shows power law behavior, but when sigma is not close to 1, we see a more complicated pattern. So in summary, we have shown that metric Palatini gravity extended by antisymmetric part of the affine curvature reduces to general relativity plus a massive vector theory, which comes from non-metricity, and we called it geometric PROCA. We constructed black hole solution of the model in the ADS background, and we constrained the geometric PROCA fields parameter using observational data on black hole. And if you are interested in this work, these are the main references that work on this model. Thank you very much.
Thank you very much. We have time for a few questions. Um,
Have you considered rotating black hole solutions in your?
No, we have a static solution, but not rotating. Yeah.
So I was just curious, how do you compare it with the Kerr solution or Kerr-Neumann in the rotating case?
You are asking if we compared with Kerr solution? No, we just compared it with Schwarzschild solution. No comparison with Kerr. Yeah.
More questions? If not, let's thank the speaker once again.